Hello and welcome to the Chapter 8 summary video. This video will focus on some of the problems from the second half of Chapter 8.
Let's start off with writing the Lewis structure for PCl3. Let's compare this to something relatively simple like NH3. So for NH3, we had began with nitrogen with a Lewis dot diagram, and then hydrogen with its dot diagram, and line them up. Now we could do this, but there are going to be some structures that are either too hard or lead to some scenarios where we have to move these electrons around a little bit that might make this process needed to be a little bit more generalized. So what if instead we take a different approach and say, well, let's count the valence electrons first. So let's count up our valence electrons. I'm going to show that we're going to get the same structure for NH3. So our valence count would be 5 for N, 3 times 1 for the hydrogens for a total of 8. For PCl3, phosphorus is in the same row as nitrogen, 5 valence electrons for phosphorus, and then 3 times 7 for the chlorines gives us a total of 26. So the next thing we want to do is find the central atom. Usually pretty easy. Usually it's the first atom listed. Sometimes it's the second if you see the atoms out in front. So it's just kind of trying to identify which atom is the central. Of course, H can't be the central atom because H only forms one bond. Halogens also usually are not going to be a central atom because they usually only form one bond as well. And there'll be a couple exceptions, and that's one of the reasons why we need these rules here. Okay, so try to find the central atom. So that's easy for these ones. Then single bond the atoms to the central atom. That's easy because that's like the least amount of bond you can have. So attach all the atoms to the central, and then give the atoms their desired octet for the non-central atoms. So don't necessarily add electrons to the central atom. So don't do anything yet for phosphorus. Hydrogen doesn't need any more electrons. So at this point we can count the electrons distributed. We've distributed 8 per chlorine. There's 3 of them. So we've distributed 24, leaving 2 electrons behind. We have 2 electrons left to go. Let's put those on the central atom because that's the only place with room left. We filled the valence shells already for the chlorine atoms. We filled the valence shells for the H as well. So the only place for our remaining 2 electrons, we've distributed 6 to NH3. The 2 electrons left over can go on that central atom as well. So we get the same Lewis structure as using a dot diagram. And then we get a very similar type structure for PCl3. Now, like I said, there will be some more complicated molecules that this type of process helps us with. HCN. Now, H to C to N is our connectivity. So here's our basic connectivity. Carbon's in the center, then nitrogen's attached to it, and hydrogen. That's why we give the compounds in this way, HCN. If we said like HNC, then it would be H, N, then C. If we need to work out how many bonds we're going to have, double or triple, where are our lone pairs, we have to count. 1 plus 4 plus 5, 10 electrons. For the isomer of this compound would have 10 valence electrons as well. Okay, so at this point here, we could do the rule, which says give all the non-central atoms an octet. If there's electrons left over, which there are no electrons left over, to go on the central atom. So there's no room for, well, I mean, there's room for electrons on the central atom, but there's no electrons available to put on those atoms. So now what we need to consider are multiple bonds. Like think about the formal charge of carbon. Carbon should have 4 valence electrons to give it a 0 charge. It only has 2 electrons surrounding it. It has a formal charge of +2. These dots are negative particles. So what do negative and positive particles do with each other? They are attracted to each other. So we can pull in electrons. So we can pull 2 electrons in, make a double bond, lose them here. Then what do we have? Well, we have a formal charge of +1. So let's do it again. And then let's perhaps move, I could have done this perhaps more thinking ahead. So if we make the double bond here, the double bond here, then we end up with a triple bond, and then we end up with formal charges. Carbon now is 4 minus 4 for 0. Nitrogen, formal charge in the final Lewis structure, carbon triple bond to N, lone pairs. So carbon's 4, nitrogen 4 minus 4, nitrogen would be 5. Think of it a 0 charge, and it's surrounded by 1, 2, 3, 4, 5 electrons. So it's 0 as well. Now what about HNC? Similar, we have a 3 plus charge. So we make one double bond, go to a plus 2, make another double bond. So we end up at HN triple bond C, lone pair on carbon. Nitrogen has a positive charge here for 5 minus 4. And then carbon would have a 4 minus 5 for a minus formal charge. Okay, and so now this is the best we can do. We started with plus 3. We got it to plus 2 with the double, plus 1 with the triple bond. Now we can't expand hydrogen to a double bond. There's only room for one bond for hydrogen, so we can't expand that octet of hydrogen and make a double bond with the H atom in any type of compound. Let's revisit CO2 and apply our rule here for drawing Lewis structures. So we counter valence electrons. 4 plus 2 times 6 is 16 valence electrons. Carbon, oxygen, oxygen. Carbon's our central atom. Satisfy the octets at the non-central atom. Calculate formal charges, or actually we will count electrons first. We've distributed 8 times 2, so we've distributed all of our electrons. So it's important to make sure we don't have any more electrons left over to put on the central atom. And so then at that point we can calculate formal charges, look at our octets. So we see we have a deficient octet and a 2 plus formal charge. So we have room for electrons around that carbon atom and a charge to pull them in. So we can pull one double bond in here. So that would go to O double bond C. Think about our formal charges now. Plus here, 0 here, minus here. So we have a positive charge still on carbon. Electrons are still negatively charged. So we can take these 2 electrons and make that double bond. So we then end up at C double bond O, lone pairs all the way around, following our rule. So 0 formal charges all the way around. So a more generalized set of rules that we're seeing here for Lewis structures, and we're getting back to the exact same Lewis structures we arrived at using more of a using the Lewis dot diagram starting point that we'd used last time. So just more generalized, this will help us with some more complex molecules. So let's look at NCS minus 5 plus 4 plus 6 valence electrons for N, C, and S, plus 1 electron for the charge. So 1 electron minus charge adds an electron. So we have a total of 16 valence electrons. Okay, so C, S, N, lone pairs. This looks a lot like CO2. Now with one difference, we might draw a bracket with a minus charge, meaning that there's a minus charge somewhere distributed on this molecule. But we have a 2 plus formal charge here. Sulfur should have 6 valence electrons. It has 7 surrounding it. That's a minus. Nitrogen should have 5 electrons surrounding it. It has 7. So we have a minus 2. Now notice the minus 2 plus 2 minus 1. If you sum up the formal charges of all the atoms distributed in your molecule, you should calculate the charge on the molecule or the ion. So minus 2 plus 2 minus 1 equals minus 1. So that's checking out. Okay, now, but we still have a problem with our structure. We have an issue that we have a minus formal charge and a positive formal charge. We have room for electrons on carbon. So let's make a double bond. Where do we want to begin the double bond with? Well, we might say, well, let's make the minus 2 lower because it's the highest formal charge. So we might make the double bond here. So that'll leave us with, let's also use this pair first. So let's take these electrons first here. So minus. Formal charge now on this carbon, or on the nitrogen, is now minus. So should have 5 electrons surrounding it. It has 6 for -1. Carbon should have 4, has 3 electrons closest to it. So formal charge on carbon is +1. So remember, our formal charge is saying cut that bond in half and count the electrons as if we have equal sharing of electrons to calculate the net charge just within the Lewis structure. So minus plus minus total up to the overall charge of minus. Okay, so this isn't a bad structure per se, but it's not the best one because we still have a positive formal charge and room to make one more bond. So which atom do you think you want to leave negatively charged, N or S? Well, probably you want to choose N because nitrogen's more electronegative. So you want to compare these electronegativities. So the electronegativity of nitrogen is greater than sulfur. So nitrogen desires electrons more than sulfur does. So when we go to make our final double bond, we're going to choose sulfur, make our double bond. So we end up with N, double bond C, double bond S, lone pairs on sulfur. Nitrogen looks just like CO2, but we had some more choices to make. We end up with formal charges of 0 on sulfur, 0 on carbon, but minus on nitrogen. Overall, minus charged as it should be. So our formal charges add up as they should. And then we're leaving the more electronegative atom with a negative charge. So we could have made a triple bond. If we had made this structure instead, imagine we used this structure. What's wrong with this one? Well, the answer would be we have a formal charge of 0 on the more electronegative atom and minus on the lesser electronegative atom. So that would be a poorer structure. This would be the best Lewis structure for NCS minus. What about O3? At first glance, O3 seems complicated because maybe we've never considered it before, but one of the O's would have to be the central. The other 2's would have to be connected to it. So the other 2 O's would be connected to the central. So give the non-central O's their octets. Let's count up our electrons. 3 times 6 for each oxygen for the valence count of 18 electrons. We've distributed 16 electrons. Means we have 2 electrons to go. We put them on the central atom. And so then at this point, we'd have oxygen with 4 electrons surrounding it. It should have 6. Plus 2 formal charge on O, and then minus formal charges on the 2 outer O's. And so then we have a positive charge and room for electrons. Our octet is not yet filled on O, so we can take 2 electrons, move them in, make a double bond. Okay, so we end up with double bond O, lone pair, single bond O, 3 lone pairs. Okay, now this would almost be the end of the story. We could, in a way, draw a box around this and say, okay, that's good. But we have the possibility, well, you could say, well, you still have a +1 charge. Can you make another double bond and go to here? But the issue is that expands the octet of that O, so that does not work. So we cannot expand octets. Generally, we can't, period. But, technically we could consider this for third row atoms. Once we get to the third row, we can consider a octet expansion, but because we're not yet in the third row, we cannot expand an octet. But what we could do is make the double bond with either of the oxygens and leave the other one as a single bond. So what's the difference between this structure here and this structure here? They're almost the same. If you label your oxygens, it's a matter of whether you have the single bond between OA and B or the double bond between OA and B. So these are equivalent Lewis structures, equivalent in what they represent, but they're not exactly the same. They're still different from each other. So now the real molecule is actually going to be a blend between the double and the single in any of these spots. So the real molecule is going to end up existing as the composite of being half the time a double bond, half the time a single bond. What does that mean? Well, if you picture ozone, the best way would be to picture it as having an extra bond half the time. So we could call these bond orders of like 3 halves. Whereas a double bond, O2 double bond, has a bond order of 2. FF single bond has a bond order of 1. The bond order, where it's half the time double, half single, is 3/2. Now this is something that's kind of complicated. There's an orbital picture we can present in the next chapter that shows this electron pair distributing themselves. So this extra double bond, in terms of that electron pair, distributes himself at all times across both of those oxygens. So this is a real-time effect that we call resonance. So this is a somewhat complicating factor, but also simplifying factor, because what it says is that each of these O's here, the OO bonds should be exactly the same. They should have the same bond lengths and the same properties. So in resonance, one Lewis structure cannot accurately depict a molecule like in the ozone molecule. So we have like resonance structure 1, resonance structure 2. The real molecule exists as a composite of the two. Okay, so when we have two different yet equivalent Lewis structures, the real molecule is a blend between the two. Notice how these bonds look exactly the same? It's because they're both describing a bond that's equally halfway between single and double. This is seen in organic molecules, like in the molecule benzene. Benzene has 6 carbon rings and a hexagonal ring. You can describe, or there are double bonds that can either be between these carbons or alternated between these carbons. And this effect of resonance is that these electrons are always distributed across the molecule. And this is probably the best depiction of benzene. Once you get to OChem, you start to replace hydrogens. Every time you see a vertex that's a carbon with the required number of H's to give each of the carbons 4 total bonds. So this structure is just interpreted to be this one here. So a simplified structure of benzene using just balls and sticks leads to this structure here, which is perhaps better drawn like this, where you're picking up that each of those carbons is not quite a double bond, not quite a single, but really a 3/2 type bond. So you have a total of, what did that? So you have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 bonding pairs of electrons. That are being distributed across the 1, 2, 3, 4, 5, 6 covalent bonds. So that's how you get your bond order of 3/2. Same thing with ozone, double bond O, single bond O, that you have 3 bonding pairs of electrons being spread across the 2 bonds for the same type of 3/2 bond. Now we're going to get into bond lengths a little bit later in terms of their lengths, but usually, especially when you're comparing exactly the same type of atom, a double bond ends up being shorter than a single bond. But all the bonds in ozone have the exact same length. All the bonds in benzene have the same length. So the length would be single, longer than double, and then 3/2 bond would be exactly in the middle for our benzene resonating bonds. So let's write a Lewis structure for carbonate ion, CO3 2-, 4 plus 3 times 6 plus 2. Now if you ever see a cation, if you have a cation like NO plus and we're counting electrons, you would go 5 for nitrogen plus 6 for O minus 1 for the positive charge for 10 electrons. So you add electrons for the charge, you take electrons away for the positive charge. So for carbonate, we have a total of 18 plus 6, that's 24 electrons. Central carbon. Oxygens, give them their octets. An octet for the last one. And so then we can calculate formal charges. Plus formal charge for carbon, 4 minus 3. 6 minus 7 for the outer oxygens. They all add up to minus 2, so minus 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 is minus 3, plus 1 for minus 2 overall. So the charges are checking out. Now we have room for one more electron, or one more bond around carbon, so we can pull that extra electron pair in, make our double bond. lose those electrons, and then we can resonate those bonds around the molecule. So then we could write that extra bond here. And then finally, we can have, and these arrows are indicating resonance. A backwards arrow indicates resonance. A resonating electron pair, it means it's resonating at all times. The molecule is never one of these structures. We're trying to write structures to understand molecules. Okay, so just because we write a structure doesn't compel a molecule to behave in any particular way. We're trying to understand how molecules behave. So the real molecule is going to exist as the composite of these three structures. What would that look like? So what's the composite structure? Well, it'd probably be the case of having a central carbon, oxygens with an extra double bond. So we have a total of 4 bonding pairs of electrons being spread across the 3 bonds. So we have 1, 2, 3, 4 pairs of electrons being spread across the 1, 2, 3 covalent bonds. For a 4/3 type bond. Okay, so this bond should be a little bit longer than a double, but then shorter than a single bond. Another thing that happens, you can consider the charges on oxygen. So the charge on oxygen in this compound, like just follow one of the O's. Let's pick this O here. So let's track the charge of this O. It's minus here, and then it's 0 here. So charge on O is either -1, or 0. That means the charge on O is -2/3 at any given moment in this molecule. The hardest part to consider with resonance is the molecule is never like this structure, or this structure, and it's just bouncing back and forth. It's all the time really the structure I'm drawing in the yellow brackets. It's at all the times the molecule that has about a 4/3 bond length or bond order for each of the bonds, and the O's all have exactly the same charge. And the formal charge on O, or on the carbon, exactly works out to be 0. So you can check your charge too. -2/3 times 2 gives an overall charge of the molecule still of -2. So the charges are checking out. Okay, let's consider some additional molecules. PCl5, 5 plus 5 times 7, 40 electrons. Now I have no choice for this molecule but to expand the octet of phosphorus. Now I said before, atoms in the second row and in the first row, like hydrogen and oxygen, cannot expand their octets. Now atoms like phosphorus are observed to expand their octets in the formation of molecules like this one. So like PCl5 exists in nature, not really in nature, I think you can make it in the lab. I don't think you're going to find this in the forest or anything like that, but the molecule PCl5 ends up existing with 5 single PCl bonds, octets surrounding all the chlorines. Now, for this molecule, this really ends up being the final Lewis structure, so that's it. 0 formal charges all the way around. P would be 5 minus 5, Cl 7 minus 7. So this has an expanded octet around the phosphorus. That's possible. We observe this in compounds third row and beyond. The explanation for why these compounds exist has to do with the relative electronegativities. They only form in cases of relatively not so electronegative atoms and then electronegative atoms attaching. So you get all these bond dipoles pointing away from phosphorus, which are actually serving to take electron density off of that expanded octet. So the Lewis structure shows an expanded octet. The real molecule is probably smarter than that. It probably makes room for the limited octet around phosphorus by using electronegative atoms to attach to the atom to pull the electrons away. Let's look at SF4. 6 is the valence count for sulfur in the oxygen group. 4 times 7 for fluorine. That's a total of 34 electrons. So 4 fluorines attach. Give the fluorines their octet. I didn't show this for PCl5, maybe it's obvious, but each of the chlorines, there's 5 of them, has 8 electrons each. So there are no electrons left over for electron pairs on phosphorus. In this case, I've distributed 8 electrons per F. There's 4 of them. That's only 32 electrons. So I have 2 electrons left to go. Fluorine's already satisfying the octet. We can't expand fluorine's octet, but we can expand the octet of sulfur. So we end up going with 2 electrons on sulfur. Interestingly, the formal charge of sulfur would be 0. The same thing with the fluorines. So 0 formal charges all the way around in this molecule. So this would be the best Lewis structure for this molecule. So the octet of sulfur also is showing an expanded octet. But again, this compound exists with fluorine atoms to pull electrons away from sulfur. So truly, sulfur is likely not expanding the octet in a real molecule. It actually is probably developing some positive charge due to the electronegative nature and the bond polarities of those individual bonds in the real molecule. So whenever we see a molecule expanding its octet, think of it as the Lewis structure has no choice but to show the expanded octet, and the real molecule has polarized bonds to make up for that type of expanded octet. Some molecules will violate the octet rule by simply having an odd electron count, such as OH and IO. So OH would have 6 plus 1 total valence electrons for 7. So we draw our single bond to with hydrogen. Lone pairs, we just don't have the extra lone pair to give oxygen its electron, give it its octet. Now, OH minus is a pretty stable molecule, so if you go to OH minus, this would have 8 electrons. And then, of course, a more reasonable Lewis structure, we have that extra electron minus formal charge. Formal charges here, 0, 0. Octet not satisfied for the O, and that's okay. What about IO? 7 for iodine, 6 for O, that's 13. So if we go with this structure here, now how do we satisfy our octets? Which one's essential? Well, let's actually think of giving, and almost starting with IO minus. If we start with IO minus, that's 14 electrons. So think about what electron you want to remove off of this structure here. Do we want to remove this electron or that electron? And let's think about the 2 possibilities. Okay, so let me actually write out the 2 different possibilities. So one of those would be this one. And then the other one would be this one. In the first example, oxygen's formal charge would be 6 minus 1, 2, 3, 4, 5, 6 for 0 formal charge. Iodine's formal charge would be 1, 2, 3, 4, 5, 6, 7, 7 minus 7 for 0. And then in the lower case, we'd have a positive formal charge on iodine, 7 minus 6, and then a negative formal charge on the oxygen. Okay, the best Lewis structure is the one that minimizes the formal charges when given options. So the minimized formal charges is generally the best Lewis structure when you have 2 alternates. So we're going to choose the Lewis structure that minimizes the formal charges. Now the only confusing part here is that oxygen is more electronegative and truly will become partially negative, and then the iodine should become partially positively charged. But the best Lewis structure is the one that shows the formal charges of both 0, and then we can think about the bond being polarized and what impact that would have on the electronegativity of O and hence the charge on oxygen. Now let's look at NO, nitrogen monoxide. So for NO, 5 plus 6, 11 electrons. If we think of NO minus, 12 electrons as our starting point, so we might think of this structure here, like O2, double bond, lone pairs all the way around. So do we want to lose an electron off of N or off of O for NO? So do we want to go to this one, or do we want this structure? Let's think about our formal charges here. So the first one, formal charge of 0 and 0 for both. The second one, minus and plus. So 5 minus 6 for N, 6 minus 3 for 5 for plus 1 for O. So why would O go positive and N go negative when oxygen's more electronegative? So this structure here makes no sense. So this is the better Lewis structure for NO. So we also then can picture oxygen being more electronegative and truly should become partially negatively charged, and nitrogen should end up being partially positively charged. Okay, we already did NO on the previous page. Not sure why it's here again, but CO, let's look at carbon monoxide. 4 plus 6, carbon. This is like N2 with only 10 electrons, where we have to go with a triple bond to satisfy the octets of both atoms. So then we end up with a positive formal charge on oxygen and a minus formal charge on carbon. So for diatomic molecules, we have to satisfy the octet rule. So satisfy the octet rule, then distribute the charge so we want to minimize the formal charges. Now there's really there's no alternate structure here. There's no way for me to flip and add, like if we want to add an electron to O, take one away from carbon, like if we want to do this, that doesn't quite work because we would be expanding the octet of O, and we can't do that. So we are limited to this Lewis structure here. Now I want to show one other Lewis structure that is kind of clever, but it just doesn't satisfy the rule that for diatomics we have to satisfy the octet rule. So this Lewis structure here is not satisfying the octet rule for carbon, because carbon doesn't have 8 electrons surrounding it. Now interestingly, the formal charge of carbon would be 0, the formal charge of oxygen would be 0. I just want to point out that this is not the best Lewis structure for carbon monoxide. Now one of the things that's true for oxygen is it's more electronegative, so it's going to try to pull the triple bond towards itself. But a property of carbon monoxide is that the oxygen remains as the partial positive atom and carbon remains as the partial negative atom. The true charge, due to the electronegativity of O being greater than C, is actually only about plus 0.02 electrons, and the negative charge on carbon is actually only minus 0.02 electrons. The dipole moment of CO is pretty small. The dipole moment is only about 0.12 dBi. So it's a pretty small, not a very polar molecule, so not a huge amount of charge being distributed, meaning the positive formal charge isn't quite as high in the real molecule, but it's still positive on the oxygen. And interestingly, when carbon monoxide gets into the air and you breathe it in, it's this electron pair here on carbon that can attack and add to an iron atom in hemoglobin and irreversibly attach. So the carbon irreversibly attaches, and it's primarily due to the negative charge that that atom has built up on it in the molecule of CO. So you get, instead of oxygen attaching to your hemoglobin, which is what's supposed to happen when you breathe, if carbon monoxide attaches, it irreversibly attaches and it doesn't come off until you make new hemoglobin molecules. So if you don't die, eventually you'll make new hemoglobin molecules and you can continue breathing, but that may not be the case if you have too high of a concentration of carbon monoxide due to this irreversible addition of carbon to hemoglobin molecules. So now we have some octet rule violations that pop up in compounds like BF3. Let's take a look at this molecule. It's a pretty interesting one. If we look at boron here, 3 valence electrons, 7 times 3 for fluorine, total of 24 valence electrons. Central boron attached to fluorines, give them their octets like usual. Okay, that's all 24 electrons. So we have none left over, so we can't satisfy boron's octet with a lone pair. So should we use a double bond? So let's think about going from this structure to one where we take a lone pair, make a double bond. So if we do that, we'd arrive at something that looks like this. Now, what's wrong with this structure? Well, what I think is wrong with this structure is think about boron. Boron's formal charge is 0. Like, it doesn't have a formal charge in our starting structure. It has room for 2 electrons, but it doesn't have any charge to pull them in. So why would 2 electrons on fluorine want to move towards an atom that doesn't have the proper charge to pull them in? Fluorine is actually trying to take the electrons in the bonding pair and pull them closer towards itself anyways. So the fluorines are actually polarizing the bonding pair electron and trying to get that pair of electrons closer towards itself. So why would it do that and then somehow still give an electron up to make a double bond? If you ask me, this is nonsense to even consider such a double bond, because you're making a positive charge on the most electronegative element on the periodic table, so the element that wants electrons the most isn't just going to willy-nilly give them up to satisfy some rule that somebody calls the octet rule. Boron here would go negative to balance everything out. So this just seems like a bad idea. The book calls these not the dominant structure, and it calls this one the dominant structure. You know, that's just because the book wants to sell books to schools with teachers who like to call this a valid option. It's not a valid option. It's a terrible option. It's wrong on many different levels. This is the best Lewis structure. Now, sometimes you see and sometimes we have to be careful on exams so you know which Lewis structure to give. This is the Lewis structure that satisfies the formal charge rule. This is the Lewis structure that satisfies the octet rule. And we'll see a couple examples a little bit later where we actually want to satisfy the octet rule and not the formal charge rule. We'll try to explain why that's the case later. But think of the rule this way. You can have an atom without an octet that's perfectly content without an octet because there's no charge on that atom to pull in multiple bonds to satisfy the octet. So boron's happy to have its octet not satisfied due to what's sometimes called the formal charge rule, or just because that's the structure that minimizes the formal charges of the atoms in that particular molecule. I like to think of it this way. If you're thinking about making double bonds, like in the case of carbonate ion, we had that positive formal charge to attract the electrons in to make that double bond. So you need the charge and the room for electrons to make a double bond. We just don't have the charge in the case of BF3. So in the case of BF3, the book says this is dominant, these are less important. I say they're not important at all. So I like to say they're not really important, even in the slightest. The elements in the second period before carbon can make stable compounds with fewer than 8 electrons, like BF3. BeF2 is another one that does this. You could argue that this would probably be better described as an ionic compound, so it's pretty close to this. But if you consider it like this, that's probably a good alternative structure as well. So it's probably somewhere between this and ionic, and definitely not going to be the case of having double bonds between beryllium and fluorine. Now, what about phosphate? Now, phosphate, I don't think it actually goes in this title. We're going to be considering more than 8 on this slide here. So for phosphorus, 5 valence electrons, 4 times 6 for oxygen, plus 3 for the charge, gives a total of 32 electrons. So let's do this one over here. Now this one ends up being tricky, but not that tricky. So we distribute 8 electrons across each of the O's. That's all of our electrons, no lone pair electrons on phosphorus. So should we make a double bond? We have a positive charge. We have the octet filled. We also have oxygens all negatively charged, which negative and positive do seem to attract. But why would we necessarily go to this structure here, which would minimize the formal charges on one of the O's in the phosphorus? So our formal charges are minimized. Here our octet is satisfied. Okay, so we have the octet rule being satisfied. We have the supposed formal charge rule being satisfied over here. Well, depending on who you ask, these structures could both be taken as the best Lewis structure for PO4. And I don't know if it makes sense to call one better or worse. I would generally lean toward this structure because I like to think of O's as keeping their negative charge. And an electronegative atom isn't just giving its electrons up easily. So I like to think of this as probably more likely towards the better answer. The textbook says how some quantum mechanical calculations seem to suggest that as well. But this is probably important enough that we say that this is probably actually important enough to recognize this type of Lewis structure. And it's the one that satisfies the formal charge rule. So if you're asked to consider the formal charge rule or to choose the Lewis structure of phosphate that minimizes formal charges, it would be the one with 5 total bonds. If you're asked for the one that satisfies the octet rule, it'd be the one with 4 total bonds. But now you have to picture resonance here, because one of the important artifacts of PO4 are that all the bonds have the exact same length. So all the bonds in PO4, if you're picturing the one with the double bonds, you just have to work a little bit harder to see that each of those bonds should be described as being a bond that has about 5 pairs of electrons spread across 4 bonds for about 5/4 bonds. And that they're all the same length. That's one of the keys. And all the oxygen should have the same charge. So the charge on each of the O's, so the real molecule, you might picture it like this. If you want to picture the formal charge rule as having this extra bond, 5/4 bonds, and the charges on the O's would be minus, 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 or 0, or about minus 3/4. 3/4 times the 4 O's gives you the overall charge of minus 3. The charge of phosphorus, again, being 0. So I think there's a lot of issues with the formal charge rule that become complicated, and you have to do a lot of mind-bending tricks to picture the charges working out to being exactly the same and the bond orders working out to be exactly the same. Whereas if you choose a structure that satisfies the octet rule, then of course all the bonds are exactly the same in length. They're all single bonds. All the O's are equal in charge. They're minus charged. Oh, by the way, if you do a relatively high-level calculation of the molecule, it suggests all the O's have charges of -1, closer to -1. So probably this is your better structure. But again, 2 different types of structures. One satisfies the octet rule, one the formal charge rule. Okay, so this, I don't know what I was doing with the header here. This header doesn't have anything to do with this molecule. Let's just look at formaldehyde. We should get formaldehyde to satisfy the octet rule. So we got the 2 hydrogens onto a central carbon as well as an oxygen. If we use our usual rule, we would go to this structure, positive formal charge, negative formal charge. Let's make a double bond. So we end up at this structure here. So this is formaldehyde. That's the best Lewis structure. We could count electrons to make sure we did this right. 1 times 2 plus 4 plus 6. That's a total of 12 valence electrons. We got to this point 2, 4, 6, 8, 10, 12. No electrons left over for carbon, so we were good with carbon. And then the double bond due to the formal charge pulling it in to make the double bond. What about acetic acid? Again, this header. I don't know what I was doing with the header. So acetic acid, CH3. C. Now what about the COOH? Well, we could think about this for a minute. Oxygen wants to form 2 bonds and have 2 lone pairs. Carbon wants to form 4 bonds. You know, like, it just doesn't work if we try to linearly attach those O's. So that doesn't quite work. So let's do something different. So let's attach both of the O's and then the hydrogen to one of the O's. So one of the things with structures that you can take advantage of is that oxygen atoms should form 2 bonds, 2 lone pairs. To have a 0 formal charge in a stable molecule, carbon should form with 4 bonds. So that leads us pretty quickly to the double bond, 2 lone pairs for O. So you can use some tricks to quickly get you into a Lewis structure. So this would be your COOH group is that acid group. Now you see this in a lot of different molecules. Like you could have two acid groups connected together, two of the carboxylic acid or two carboxylates. That's oxalic acid. So this is oxalic acid. You could have vitamin C, which has three groups that look like this. So that's our acidic group. So this hydrogen here is acidic, can be removed with base. These hydrogens here are not acidic. They're not coming off when you add base to the solution. So as you recall, we talked about bond energies in Chapter 5. This is re-showing that chart. It comes back up again in Chapter 8. In fact, this used to only be taught in Chapter 8. Let me point a couple things out that are somewhat useful to compare and consider. Look at CH compared to OH compared to FH. Where's HF? HF's over here. So what's this trend here? C to O to F. That's the atom becoming more polar. That's the bond becoming more polarized. Look at how that has an effect on the bond strength of HF. And also look at HF, the HCl, HBr, HI, dropping lesser polar, longer bonds. So bond lengths are related to sort of the polarity. The more polar the bond, the more ionic, the closer we're strengthening that bond to something like it is in, say, LAF or NaCl, which have bond strengths closer to 800 kJs per mole. So we're increasing our bond strengths when we increase the polarity of the bond. If we also compare a couple bonds where we just make the bond longer, like ICl, IBr, I2, generally longer bonds end up being weaker as well, with the idea being you're just spreading out those electrons that are being shared. Now, another artifact that's probably obvious, but if you look at a CO single versus CO double, the double bond's stronger because you have 4 electrons holding the atoms together instead of 2. Then if you look at, and then the bond also shrinks as well, so the bond is actually shorter for the CO double bond. Likewise, we can see, where's one more example, that O single versus OO double, that the bond strengthens for the double bond as well. Let's see if there's any triple bonds on here. And then triple bonds not on here, but the nitrogen-nitrogen triple bond is a very stable bond due to being a triple bond. So bond enthalpy and length are connected together. Multiple bonds are stronger than single bonds. We can also measure the average bond length for a different type of bond. So let's look at the nitrogen-nitrogen triple bond. Strongest bond, so this is looking at the bond enthalpy, this is looking at the bond length. So we have the shortest bond, that's the strongest. If you lengthen the bond, you weaken the bond. Lengthen the bond some more to the single, you weaken it even more. So let's compare according to their Lewis structures that satisfy the octet rule to rank the bonds in the following molecule by increasing length. Okay, so let's start with SO3. So SO3, 6 plus 3 times 6 for 24 valence electrons. So that'll be a sulfur, oxygen, 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 lone pairs all the way around. Then that's it. That's all 24 electrons, none left over. And so then we have a 6 minus 3, a 3 plus formal charge, so we can make a double bond. Okay, so we make a double bond, and then we can have that resonating bond, so we have a 4/3 bond here in our molecule once we take into account resonance. Now, SO2 3 minus, or SO3 2 minus, put that backwards. So that would be 6 for sulfur, 3 times 6 for O, plus 2 for the charge. So that's 18 plus 8, that's 26. So that's going to be a central S. The O's satisfy their octets. That's only 24 electrons. So there's 2 left over. Let's put them on sulfur, the only place for more electrons. So leftover electrons go on the central atom. We're satisfying the octet rule. So it says according to their best Lewis structures that satisfy the octet rule. So we're satisfying the octet rule, 4/3 bond. We're satisfying the octet rule, single bonds. So that's 3 bonding pair electrons spread across the 3 bonds. So these are all single bonds. SO4 2 minus. I'm going to throw in one more, the SO double bond. Well, we'll see it's double in a minute, but SO. It's kind of go too, but with sulfur and oxygen. So for SO4, 2 minus, central sulfur, 4 oxygens. We didn't add these up, but it's 6 plus 4 times 6 plus 2. That's 32 electrons. So that's electron pairs all the way around. None left over. We're satisfying the octet rule. So we have single bonds. Okay, and then finally we have SO double, or the SO. Let's work out that it's double because it's for SO 6 plus 6. So S double bond O, lone pair just like O2 for a double bond. Let's rank these bonds. So we should have the SO double be the shortest because it's the double. SO4 2 minus, SO3 2 minus in the middle, being very similar. And then finally, SO3 without the charge being, oh, no, sorry, let's backtrack this for a minute. The double bond, the bond order here is 2 electrons being spread across the 2 bonds. So SO is the shortest, then SO3, because it's the 4/3 bond, and then SO4 2 minus, and then SO3 2 minus. Ranking them based on their bond orders, they would be similar due to having exactly the same bond order. So their bond orders are both 1. Now, one interesting artifact is that the formal charge of sulfur here is positive. You have minuses all the way around. And then this formal charge is +2, and then minuses all the way around. So we would probably expect SO4 2 minus to be slightly shorter than SO3. So you're probably going to expect this trend if you inspect formal charges. And I think then that makes sense with their actual bond lengths for the real molecule. Okay, so that gives us a sense of how we can write Lewis structures and compare the bond lengths as a function of the bond type. Double bonds shorter than single bonds. 4/3 bonds would be right in between. So the main idea here is your double bond shorter than a single bond. And then like a 3/2 or a 4/3 would be right in the middle. So the 4/3, somewhere between single and double. So it's somewhere in between the length of a single and a double. All right, that's all for the second half of Chapter 8. Thank you for the attention.
Let's review some of the learning objectives from Chapter 8. We should be able to write Lewis symbols for atoms and ions. So that's as simple as things like chloride ion, picturing that as our Lewis dot symbol. Define lattice energy and be able to arrange compounds in order of increasing lattice energy based on charges and sizes of the ions involved. So the closer we can make a plus and a minus, the better. So smaller ions have higher lattice energies. As well, more highly charged ions, a 2 plus and a 2 minus, will have a higher lattice energy as well. So we want smaller ions and more highly charged ions to have greater lattice energies. We might then recall that lattice energy was not directly measured in the lab, but rather we determined lattice energies through something called a Born-Haber cycle. We'll probably see a few review problems of that topic later in lecture. But we can also use atomic configurations in the octet rule to draw Lewis structures for molecules. We see a lot of different examples of Lewis structures. Sometimes we might use the idea carbon forms 4 bonds. So if we have a molecule like CH2O, maybe we're just using the general idea 4 bonds to carbon, 1 for each of the hydrogens, 2 bonds and a lone pair for oxygen. We could also count electrons and apply a more rigorous set of rules for molecules that maybe aren't organic in their nature. Some of the organic compounds are a little bit easier to sketch Lewis structures of. If the examples are a bit more complicated, then we're counting valence electrons, distributing the electrons to the outer electrons or the outer elements first as they're connected to their central atoms, counting electrons up to see if there's any leftover electrons to place on the central atom, and kind of going from there to see if we need to make multiple bonds as a basis of the formal charges of the atoms, and maybe also noting the octet rule if we need to satisfy the octet rule for the molecule is something we may be considering. We can then use electronegativity differences to identify nonpolar covalent versus polar covalent versus ionic bonds. Ionic bonds are the elements that are far separated on the periodic table, so they have a big difference in electronegativity. Polar covalent kind of in the middle in their electronegativity difference, and nonpolar covalent have a non-electronegative elements involved in their bonds, or maybe sometimes exactly the same atom. Like a nonpolar bond, the best example is something like a chlorine-chlorine bond, something where you have the exact same nuclei that's going to pull equally on both sides of that bond, and the bonding pair electrons have to be equally shared. This also happens whenever you have some relatively non-electronegative elements. Something that we haven't talked much about in class is if you take some of the most electronegative elements like NOF, sulfur, chlorine, and bromine, and pair these elements up with just about anything other than themselves, then the molecule is going to have to be polar. There's a couple tricky examples, like N and Cl happen to have exactly the same electronegativity, but it does turn out that an NCl bond is kind of polar. So I mean, a simple rule would be if you have any of these atoms of the more electronegative elements of NOF, SCl, Br, that if they're paired up with anything other than themselves, then you know that that has to be something you'd classify as a polar covalent bond. A better question we tend to ask is which bond is more polar. The more highly separated the elements, the better. So if you're judging elements, you'd want to pick elements that are furthest away to be the most polar. Like the PF bond is going to be more polar than the NF bond, and the NF bond is going to be more polar than the OF bond. So as the elements get closer together, their electronegativity differences won't be as high. So you want far separated elements to have an increase in their electronegativity differences. We can calculate the charge separation in diatomic molecules as a basis of the dipole moment and the bond length of the molecule. So we have this relationship between dipole moment, charge, and bond length. Only issue here is it's a unit conversion problem. We take a charge in coulombs, bond length in meters, we get a dipole moment in coulomb meters. We see that often we use this unit of Debye to change into a non-SI unit, where the conversion is 3.34 times 10 to the minus 30 coulomb meters is equal to 1 Debye. So you just have to make a conversion and think about our units here, and we can relate charge and bond length to this dipole moment. So we can calculate formal charges from Lewis structures, and then use those formal charges to help us identify the best Lewis structure for a molecule. For a formal charge, we're just cutting bonding pair electrons in half and assigning half the electrons to one atom, the other half the electrons to the other atom. And so in like CH2O and formaldehyde, we have 0 formal charges for all the atoms in this molecule. All the formal charges should up to the overall charge in the molecule or the ion. So we want to recognize molecules where resonance structures are needed to describe the bonding, and it's really important for us in molecules like ozone, other molecules like this, where we write a Lewis structure. If we come to this Lewis structure here, that this Lewis structure is only one of 2 that are important to understand the bonding in ozone. So when we realize that we could have made the double bond between the other 2 oxygen atoms, that we have a case where the molecule is actually never going to exist as structure A or structure B. So it's never going to be A, it's never really going to be B. Whenever we have this case where the molecule can be shown with Lewis structures that are different yet identical in what they're representing. So these are identically the same Lewis structures, say, in terms of the energies of the molecules. There's no difference energetically in either of the 2 structures. The only difference is which atoms are making the double versus single bonds. The real molecule is always going to exist as the composite. So the real molecule is always going to be the composite structure of these 2 Lewis structures. So the bonds between the 2 O atoms are best described as being the exact same length because they're the exact same type of bond. The type of bond here, I would describe this as a 3/2 bond. So it's not really a double, not a single. I'm taking the 2 plus 3 pairs of electrons and spreading them across the 2 actual OO bonds. So the number of pairs of electrons that are being shared across the number of bonds. So I've got 3 electron bonding pairs spread across the 2 OO bonds. So I get the 3/2 order. Now if you pick up, like, for say nitrate, you have a double bond OO with this molecule. and you could sketch 3 different Lewis structures that are all equivalent in what they're representing, then you have 2, 3, 4 pairs of electrons being spread across the 3 NO bonds. So that bond order, I would say, is 4/3 in a molecule like NO3 minus for nitrate ion. Now, we want to recognize exceptions to the octet rule. So the octet rule is sometimes satisfied by molecules that are deficient of an octet, like BF3. So a molecule like BF3 ends up being deficient of an octet. Fluorine satisfies the octet rule by having lone pairs surrounding it, but then boron is deficient of an octet within this Lewis structure. 0 formal charges around, so there's no charge to draw in a double bond, and there's no need for a molecule like boron to satisfy an octet rule. So it's fine with an octet being less than an octet here, because we have 0 formal charges for all the atoms, and then to satisfy boron's octet would either require electrons we don't have to distribute within this molecule, or it would require making a double bond from an atom that really wants to keep its electron pairs. Okay, finally, we want to predict the relationship between bond type, single, double, triple, and bond strength and bond length. So our single bonds are generally the longest, double are shorter, and then triple or even shorter in their sort of length. So we're thinking of the lengths of bonds. Our single are the longest, then double, shorter, triple, or even shorter. So if we have a triple bond, say between 2 carbon atoms, we have 6 electrons to hold the atoms together. That's going to be much shorter in length than, say, if we only had 2 electrons to hold the atoms together. And then that's going to strengthen, these electrons are going to strengthen the triple bond. So our triple bonds are stronger and shorter. The single bonds are longer and weaker. So we have that fundamental relationship between bond lengths and strengths as discussed towards the end of chapter 8. So that's all for this video. Thank you for the attention.